Good morning, student. Today we are going to discuss the topic of application of vibrational rotational spectra. From the vibrational rotation spectra, it is possible to calculate distance between the two lines in a P or R branch. This separation is equal to twice B. Also, B is related with moment of inertia, that is B is equal to H divided by 8 pi square IC. And one can calculate moment of inertia. Moment of inertia is related with bond length by this equation, that is I is equal to mu R0 square. Hence, one can calculate bond length of the molecule. From your vibrational rotational spectra, one is able to calculate bond length of the molecule. Another application of vibrational spectroscopy is in the calculation of force constant. It is important, that is K. It is related to vibrational frequency by the equation omega E is equal to 1 by twice pi under root of K divided by mu. This equation is only applicable when vibrational frequency is given in second inverse. If we divide this equation by C on both the sides, so omega E by C, it is converted into nu bar. So this equation is used when vibrational frequency is given in centimeter inverse or meter inverse, where mu is reduced mass. So now we are going to solve some numerical based on vibrational spectroscopy. The fundamental vibrational frequency of SCR is 2890 centimeter inverse. Calculate force constant of this molecule. The atomic masses of hydrogen is 1.673 into 10 raised to the power minus 27 kg, and chlorine is 58.06 into 10 raised to the power minus 27 kg. So we have to calculate force constant K. Just see that fundamental frequency is given in centimeter inverse. So we can convert that centimeter inverse into meter inverse. Just multiply this quantity with 100. So it is equal to 2.89 into 10 raised to the power 5 meter inverse. Since atomic masses is directly given, so there is no need to divide this with Avogadro number. When molar mass is given, then only divide molar mass by Avogadro number. So atomic mass is directly given. For hydrogen, it is 1.673 into 10 raised to the power minus 27 kg. For chlorine, it is 58.06 10 raised to the power minus 27 kg. So first of all, calculate mu. Why? We have to calculate mu first, because the formula which we are going to use, it is equal to K is equal to 4 pi square C square nu bar square mu. So mu is reduced mass. So we have to first calculate mu. So put all the value. We comes with 1.626 into 10 raised to the power minus 27 kg. This is the value of reduced mass. So now calculate force constant K. Since frequency given in centimeter inverse, we can use this formula. Don't use this formula. Use this formula. So that formula is rearranged and written like this. After putting all the values, we come force constant is equal to 482 Newton meter inverse. 1 Newton is always equal to 1 kg meter second square. Now we are going to solve second numerical. The force constant of CO is given, that is 1840 Newton per meter. We have to calculate vibrational frequency in centimeter inverse. Atomic mass of C12 is given, that is 19.9 into 10 raised to the power 27 kg. Atomic mass of oxygen is also given, that is 22.6 into 10 raised to the power minus 27 kg. Since we have to calculate vibrational frequency in centimeter inverse, so first of all we have to calculate reduced mass. So formula of reduced mass is m1 m2 divided by m1 plus m2. Put all the value of reduced mass comes as 11.4 into 10 raised to the power minus 27 kg. In numerical they say calculate vibrational frequency in centimeter inverse. That's why this formula is used. So nu bar is equal to 1 by twice pi under root of k mu. Value of k is given, mu value, that is reduced mass value is calculated. Put all the value in this equation, we comes with this value, that is 2.132 into 10 raised to the power 5 meter inverse. Convert meter inverse into centimeter inverse, so we comes with 2132 centimeter inverse. So in next numerical, calculate force constant of HI bond if its vibrational frequency is 6.6 into 10 raised to the power minus 3 second. Just see the unit of vibrational frequency, it is given in second inverse. Reduced mass of HI is given, that is 1.648 into 10 raised to the power minus 27 kg. Since vibrational frequency is given in second inverse, we choose this formula, that is k is equal to 4 pi square omega e square mu. So omega e value is given, that is 6.6 10 raised to the power minus 3. By putting all the value, force constant of k comes as 283.49 centimeter inverse. Now we are going to see degree of freedom and normal modes of vibration. It is a very important topic. There is sure short question on this topic up to the 4 mark. The number of variables required to locate all the atoms in a molecule is called degree of freedom. For a single atom, only 3 variables, that is x, y and z, are required to locate it. However, for a polyatomic molecule containing n atoms, total number of degree of freedom are given by thrice n. This degree of freedom include translational, vibrational and rotational degree of freedom. Degree of freedom of a molecule play important role in determining normal mode of vibration and number of fundamental bands of absorption. Normal mode of vibration is defined as a molecular motion in which all the atoms in the molecule vibrate with the same frequency and all the atoms pass through their equilibrium position simultaneously. Polyatomic molecules are classified into 2 categories. First is non-linear molecule and second one is linear molecule. So we are going to see the topic of non-linear molecule. These molecules have 3 translational degree of freedom along x, y and z axis because position of atom changes with translation of molecule. Also they have 3 rotational degree of freedom along the three axes. Remaining are the vibrational degree of freedom. So total degree of freedom is equal to thrice n. Translational degree of freedom is thrice. Rotational degree of freedom is thrice. So vibrational degree of freedom is thrice n minus 6. So for non-linear molecule, thrice n minus 6 normal mode of vibration, and so thrice n minus 6 fundamental bands of absorption. So this formula is very important. Generally numericals ask on these formulas. Now we are going to see linear molecules. These molecules have 3 translation degree of freedom along x, y and z axis because position of atoms with translation of molecule. They have only 2 rotational degree of freedom because rotation about molecular axis does not change the position of atom. Remaining are the vibrational degree of freedom. So total degree of freedom is thrice n, translational degree of freedom is 3, rotational degree of freedom is 2. So vibrational degree of freedom is thrice n minus 2 minus 3, that is thrice n minus 5. Hence linear molecule has thrice n minus 5 normal modes of vibration, and so it have 3s minus 5 fundamental bands of absorption. In our next class, we are going to see the topic of normal modes of vibration of triatomic molecule. Thank you very much.